What if time is just an illusion? For thousands of years, humanity has perceived time as something unshakable, a river flowing from the past to the future. We measure it with clocks, mark its passage with calendars, and structure our entire lives around it. However, deep within modern science, a startling idea is emerging. Perhaps time is not a fundamental component of reality, but merely a byproduct of deeper laws of nature. Could time be something that emerges, rather than something that exists from the outset? And if the fundamental equations of the universe don't actually require time, does that mean that past, present, and future are merely illusions of our minds? These questions lead us to a radical re-evaluation, not only of physics, but also of the very nature of perception itself. If time is not the foundation of being, but something generated by quantum processes, what does that mean for our free will, our memory, and even the essence of human existence? If this topic resonates with you, like and subscribe. Time is a familiar and understandable phenomenon to everyone. We measure it with clocks, note the passing of days, and perceive it as something self-evident. However, from a scientific perspective, it represents a complex concept that remains not fully understood. Why does time move in only one direction? Is it possible to reverse it? In everyday life, time marks changes, but on a fundamental level, it can be seen as a sequence of moments, like frames on a film strip. We perceive these frames in a strict order, and this is not accidental. While physical laws, such as Newton's equations, do not distinguish the direction of time, reality is structured differently. The key to understanding this phenomenon is the concept of entropy. According to the second law of thermodynamics, entropy, measuring disorder in a system, always increases. This sets the arrow of time. For example, if you throw ice into water, it melts, and returning the water to its original state without additional energy input is practically impossible. The universe is moving towards a state of maximum disorder, and this defines the irreversibility of time. However, there are exceptions. Photons, traveling at the speed of light, effectively do not experience the passage of time. According to Einstein's special theory of relativity, for them, the journey from a distant star to Earth occurs instantaneously. This shows that the perception of time depends on the conditions of motion. The question of whether time can be reversed remains hypothetical. There are theories suggesting that certain distortions of space-time, such as near black holes or through wormholes, might allow this. However, there is no evidence for such phenomena so far. Imagine a river flowing from its source to its mouth. We are in a boat. The past is the path already traveled. The present is the point where we are now, and the future is the unknown waters ahead. We cannot change the river's flow, but we can study it. Perhaps one day, our understanding of time will cease to be a mystery. Throughout the history of science, time and space have been viewed in different ways. Isaac Newton introduced the concept of absolute space and time, which, in his view, existed independently of material objects. He compared them to a container for everything that exists. Yet in the 20th century, Einstein showed that space and time are not absolute, but are interrelated and dependent on the observer's motion. Time remains one of the most mysterious categories in science. Despite the familiar sensation of its flow, the fundamental nature of time has not yet been fully revealed. How does the many worlds interpretation explain the connection between the probability of quantum events and the structure of reality? What experimental evidence supports the idea of interaction between parallel branches of the multiverse? And what consequences for our understanding of time and causality arise from the block model of the universe? Modern research in quantum mechanics and the many worlds interpretation presents revolutionary views on the nature of time and the structure of the universe. One of the key concepts is the multiverse model, proposed by Hugh Everett and developed by David Deutsch, which treats quantum processes as branching histories that coexist and interact at a fundamental level. In the traditional interpretation of quantum mechanics, observation leads to the collapse of the wave function. However, The many worlds interpretation asserts that all possible outcomes of a quantum measurement continue to exist in separate branches of reality. These branches form a complex structure of the multiverse, where different versions of the same system exist in parallel, remaining isolated on a macroscopic level. Interestingly, macroscopic reality, despite its quantum nature, largely obeys the laws of classical physics. This is because the probability of different outcomes depends on the amplitude of their corresponding wave functions, reflecting an objective measure of the thickness of the branches of the universal wave function, rather than the subjective knowledge of the observer. A key aspect of the many worlds interpretation is the idea that events in one branch of reality may be determined by the existence of nearby branches. This undermines traditional views of linear causality, as the future and past become inextricably linked through a complex system of quantum interactions. This also leads to a re-evaluation of the concept of time. Instead of perceiving time as a linear flow, this model proposes the view of time as a static structure, the so-called block universe, where past, present, and future exist simultaneously. The division between these states is more a result of cognitive perception than an objective physical phenomenon. One of the most striking examples demonstrating the validity of the many worlds interpretation is the delayed choice double-slit experiment. This experiment shows that measurement outcomes can be correlated with future actions of the observer, which is difficult to explain within the framework of traditional quantum mechanics, but naturally follows from the multiverse model. Additionally, the concept of entropy is examined. In classical physics, entropy is interpreted as a measure of disorder, in statistical mechanics, as the number of possible microstates of a system, and in quantum mechanics, as a measure of entanglement. The many worlds interpretation integrates these three approaches, offering a deeper understanding of thermodynamic processes and their connection to the quantum structure of reality. How might quantum entanglement influence our understanding of time and its relationship to thermodynamic processes? According to a new study published in Physical Review A, time may not be a fundamental quantity of the universe, but rather an illusion arising from quantum entanglement, a peculiar phenomenon that links distant particles. This hypothesis could help solve a problem that hinders the development of a theory of everything, a unified model combining quantum mechanics and relativity. The differences in the description of time in these two theories present a significant obstacle to constructing a single physical framework of the universe. According to the authors of the study, one of the key challenges in quantum theory is what is known as the problem of time. To address this, the physicists applied a theory known as the Page-Wouters mechanism, proposed more than 40 years ago. According to this concept, the sensation of time passing arises in a system due to its quantum entanglement with another system, acting as a clock. Without this entanglement, the system perceives the universe as unchanging and static. In the experiment, the scientists applied the Page-Wouters mechanism to two quantum systems that were entangled but not interacting with each other. It was found that their evolution could be described by the Schrödinger equation, confirming the hypothesis of the quantum nature of time. Additional calculations showed that this principle also works for larger objects. The authors of the study believe their approach reconciles the concept of time with both quantum and classical physics. However, their work is purely theoretical, and many scientists remain skeptical of it. Currently, there are no methods to experimentally verify the quantum nature of time. Some physicists suggest the existence of particles that move faster than light, which contradicts current physics. However, the authors of the recent study believe such hypothetical faster-than-light particles can be reconciled with Einstein's theory of relativity. If time does not actually exist, how would that change our understanding of space, life, and even consciousness? The idea that time doesn't exist might sound strange, as we are used to orienting ourselves around time in everyday life. We sleep and wake up according to clocks, live in the present, and plan for the future. But what if everything we know about time is just an illusion created by our perception? Half a century ago, physicists John Wheeler and Bryce DeWitt proposed a revolutionary idea that was initially met with skepticism. They created the grand equation, which fundamentally changed the understanding of time. In their theory, time ceases to be an absolute quantity. That is, there is no hard boundary between the past, present, and future. These concepts are conditional, and in reality, the entire universe exists in one unified space-time continuum. But if time doesn't exist, what does that even mean? The answer is that everything that exists, including us, exists simultaneously, in one moment. But our perception processes this reality linearly, through the lens of past, present, and future. It's similar to how our brain is programmed to perceive events as sequential, even though they may actually exist simultaneously. John Wheeler, one of the creators of this theory, said, "Time has never been, isn't, and never will be. It exists only in our heads and in the equations we use every day." In reality, according to scientists, processes in the universe are not required to follow strict periodicity, as we tend to believe. Everything happens simultaneously, and our brain creates the illusion of time by trying to organize events. How might loop quantum gravity and string theory evolve in the future to reveal unknown aspects of the nature of spacetime that we are currently unable to observe? Loop quantum gravity is one of the theories of quantum gravity based on the concept of discrete spacetime. The theory suggests that physical excitations of spacetime at Planck scales have a one-dimensional nature. According to this theory, space and time are discrete, composed of small quantum cells that are connected in such a way as to form a colorful, discrete structure at small scales. At larger scales, this structure smoothly transitions into continuous, smooth spacetime. One possible consequence of this theory is the hypothesis of a pulsating universe. In the 1980s, this theory was developed by Lee Smolin, Abhay Ashtekar, Ted Jacobson, and Carlo Rovelli. Based on the concept of discrete space-time, the theory allows for the description of processes occurring at Planck scales and may explain phenomena such as the origin and evolution of the universe. In a modified version of his work, Bilson Thompson acknowledges that his model faces unresolved issues such as the mass spectrum of particles, spins, and Cabibbo mixing. Additionally, a later article describes the dynamics of brains using Pachner transitions, which is another step in the development of the theory. String theory is a theoretical concept that examines the interaction of objects not as point-like particles, but as one-dimensional extended objects, known as quantum strings. According to this theory, all elementary particles and their fundamental interactions arise from the vibrations and interactions of ultra-microscopic quantum strings, which exist at scales on the order of the Planck length, 10 to the negative 35th power meters. String theory emerged in the early 1970s in connection with the interpretation of Gabriele Veneziano's formulas, which were related to string models of the structure of hadrons. In the 1980s and 1990s, string theory experienced rapid development, and at that time it was expected that a unified theory, or theory of everything, would be formulated based on it, a quest that Einstein dedicated decades to. However, despite significant efforts, experimental confirmation of the theory has not been achieved, and searches for its components, such as supersymmetry, at the Large Hadron Collider, have not been successful. One of the main problems in attempting to reduce string theories with 26 or 10 dimensions to 4-dimensional physics is the vast number of compactification possibilities for extra dimensions, which can only be resolved through complex mathematical models. Additionally, string theory is criticized for lacking clear predictions that could be experimentally verified, raising doubts about its status as a scientific theory. Some scientists question its scientific value, as it is difficult to test this theory using current technologies and methods. One of the main problems is the so-called landscape problem. In 2003, it was discovered that there are a vast number of ways to reduce 10-dimensional superstring theory to a 4-dimensional effective field theory, leading to a large number of possible low-energy world variants. These variants are called the string theory landscape, and their number can reach 10 to the power of 100, or even be infinite. Moreover, within this hypothesis, the problem of computations persists. String theory largely relies on perturbative methods, and the non-perturbative formulation of the theory is still undeveloped. As a result, unresolved issues remain related to the calculation of string scattering amplitudes for more complex Feynman diagrams. Another important issue is the lack of definitive predictions for critical experiments. This leaves string theory at the stage of a hypothesis, requiring further development and the search for new methods of verification. The question of the nature of time goes far beyond the scope of a purely scientific discussion. It touches upon the philosophical foundations of our perception of reality and challenges our conventional notions of the past, present, and future. If time is merely an illusion created by quantum processes, how should we change our perception of life, free will, and responsibility? This is not just a question for scientists, but for each of us. In practice, such discoveries could lead to revolutionary changes in technology and science. The emergence of time may open new horizons in quantum computing, navigation, and information technology. These ideas could lead to the creation of innovative technologies that will reshape our future. Don't miss further research and updates on this topic. Subscribe to the channel and stay tuned for new discoveries.